Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class we were discussing about KKT conditions or the first order conditions when we have constraint optimization. So, we will be continuing that discussion today also. Let us take a look at an example for that case. Suppose we have to minimize the following optimization problem. So, we have this objective function z, that is a function of x1 and x2 here, and it is subject to this constraint x1 plus x2 greater than equal to 2. Okay. So, this same objective function we have seen another example before also. The only difference is that now we also have this constraint x1 plus x2 greater than equal to 2. Okay. In the previous example, when we had the same objective function, that was we were focusing on unconstrained optimization. So, when we had to find the stationary point for that problem, we had find this point 0 comma 1 as the stationary point, but now you can see that this point 0 comma 1 is not a feasible point because it does not satisfy this constraint. 0 plus 1 is not greater than equal to 2. So, this solution of the unconstrained optimization problem need not be feasible for the constrained optimization case. So, therefore, we need to have a different approach to find the stationary point when there is constrained optimization, and that is why we have derived these KKT conditions for finding the stationary point. So, let us write down the KKT conditions for this example problem. So, this is the first condition, 2x1 star plus 2x2 star minus 2 equal to u. So, how is this coming? So, if you recall, this LHS is coming because we have this derivative of the function z with respect to x1, and that is equal to the linear combination of the derivative of the binding constraints. Now, in this example, since there is a single constraint x1 plus x2 greater than or equal to 2, so there is a single u variable here, and this u times the partial derivative of the function g with respect to x1. So, that is getting multiplied with this u. So, now our function g is equal to x1 plus x2, okay, because the constraint that is given to us is x1 plus x2 greater than or equal to 2. So, this is our g function x1 plus x2. So, the partial derivative of this function g with respect to x1 is equal to 1, and that is why this value is equal to u times 1, and it is shown to be u here. Okay. Similarly, this one is the partial derivative of this objective function with respect to x2, and this is what it comes out, and this is u times the partial derivative of the function g with respect to x2. Again, u times partial derivative of g with respect to x2 is u times 1, because the partial derivative of this function g with respect to x2 is also equal to 1. So, that is why again we have u here. And why we have written x1 star x2 star here? Because x1 star x2 star are the stationary point which we want to find. Okay. Then we have this condition that u times 2 minus x1 star minus x2 star is equal to 0. Okay. And there is single such condition of this type because there is a single constraint that we have. Then the stationary point should be a feasible solution. So, we have this constraint that x1 star plus x2 star is greater than or equal to 2, and this variable u should be greater than or equal to 0. Okay. Now, we need to find those values of x1 star, x2 star in u which satisfy this solution. Okay. So, that point x1 star comma x2 star will be the stationary point or the solution of the KKT conditions, or the solutions of the first order conditions, or the solution of the necessary conditions for this optimization problem. Okay. So, since we know that u has to be greater than or equal to 0, we will be considering two cases in order to find the solution. First, let us assume that u is equal to 0. Okay. So, when we do that, then the first condition that we get is this thing, that 2x1 star plus 2x2 star minus 2 is equal to 0, and the other equation that we get is 4x2 star plus 2x1 star minus 4 equal to 0. Okay. So, we have these two equations with us, and we have two variables x1 star and x2 star that we want to find. So, when you will be solving that, you will be getting this solution 0 comma 1. So, this is the same case when we did not have any constraints in the example before. Why? Because when we are assuming that u is equal to 0, so then we get the same conditions that we had for the case when there were no constraints. Okay. Now, as we know already that this solution 0 comma 1 is not a feasible solution. So, our assumption that u is equal to 0 satisfies the set of conditions is wrong. Okay. So, this is wrong. So, let us then consider the remaining case that u is greater than 0. Now, if u is greater than 0, then this condition implies that 2 minus x1 star minus x2 star is equal to 0. So, this is the first equation that we get, and we get another equation by replacing the value of u from these first two equalities. That is, we will get this equation here 2x1 star plus 2x2 star minus 2 is equal to 4x2 star plus 2x1 star minus 4. Okay. So, we have this as the first equation and this as the second equation. Again, we have two variables to solve for and two equations. So, when you will be solving that, you will be getting this solution that x1 star and x2 star are both equal to 1. And when we put these values of x1 star and x2 star in any of these equations, suppose you put it in this, then you will be getting u is equal to 2. Okay. So, this solution is the stationary point of this optimization problem that is given. Okay. Okay. Now, the first order conditions or the KKT conditions that we have seen until now was for the general optimization problem, where the optimization problem was of this form that we are minimizing a function z subject to constraints gjx greater than equal to bj for all constraints j. Okay. But the type of optimization problems that we will be focusing on in static traffic assignment here will be of this form. They will be having non-negativity and linear equality constraints. Okay. So, this is a special category of optimization class within the general category of optimization problems that we have seen until now. Okay. So, the static traffic assignment problem will be a special category of optimization problem where you will be having all the constraints as either the non-negativity constraints or we have linear equality constraints. So, this is what we mean. So, we have this function minimize zx subject to, so this is the set of linear equality constraints. So, you can see that here instead of gjx we have this linear constraint given to us summation hij xi over all I is equal to bj. Okay. And then we have these non-negativity constraints here, that is xi is greater than equal to 0 for all I. Okay. So, what we will be doing here is that we will be simplifying the KKT conditions that we had derived in the previous lecture for this class of optimization problem. Okay. So, this is a special class of the general optimization problem that we have seen until now. So, we will be simplifying the KKT conditions if the optimization problem is of this form. Okay. So, before that, let us just quickly take an example of the optimization problems that we will be focusing on. So, this is this function z here, which is a function of x1 and x2. So, suppose this is an objective function here subject to this constraint here 3x1 plus x2 equal to 1 and x1 greater than equal to 0. Okay. And we also have x2 greater than equal to 0. So, this is an example of a linear equality constraint, and these are examples of non-negativity constraints. Okay. So, now let us simplify the KKT conditions for optimization problems that have non-negativity and linear equality constraints. Now, note that these linear equality constraints can be written in this form. So, they can be split into the set of two inequality constraints. First is this set, that is summation hij xi is greater than equal to bj for all j, and then this is the other one, that summation hij xi is less than or equal to bj. Okay. So, this we have seen before also, this kind of splitting. Now what we will be doing is that for this set of constraints we will be multiplying by -1 on both the sides, so that this set of constraint also transforms to the constraints where we have greater than equal to. Okay, so this is what we get here. Why are we converting this original linear equality constraint that we had into this form? Because the general optimization problem form that we had seen before had constraints of this form, that is Gj x greater than equal to Bj. Okay, so we are converting this linear equality constraint into this form. Okay, therefore the KKT conditions can be written as follows. So now we are writing down the KKT conditions for this optimization problem where we have linear equality constraints, that is summation hij xi equal to bj, and we have non-negativity constraint that xi greater than equal to 0 for all I. Okay. So now let us go slightly slowly here. So you will see that now there are 3 terms here on the RHS. LHS is not surprising here because this is the partial derivative of the function z with respect to the variable xi. But why do we have 3 terms here on the RHS? So this first term here is coming from this set of constraint, that summation hij xi, this is over all I, is greater than equal to bj for all j. Okay, so this is one set of constraints that we have, right? Now here, since gj is this function here, so when you take the partial derivative of gj with respect to xi, you will be getting hij. Okay, and that is why this uj is getting multiplied by hij. And then since we have these capital J constraints, I mean the number of such constraints are capital J, so that is why there is this summation which is going from 1 to capital J. Okay. Now we also have another set of constraint minus summation hij xi greater than equal to minus bj, again for all j in 1 till capital J. Okay, so again now this is again another g dash j function here which is equal to minus summation hij xi. So when you take the partial derivative of g dash j with respect to xi, what you will be getting? You will be getting minus hij. Okay, so that is why there is a minus sign here, and then we have hij, and we have these parameters uj dash for every constraint j, and since again the number of such constraints are capital J, so that is why there is a summation here. Okay, now let us come to this last term here. We also have these non-negativity constraints, that xi is greater than equal to 0 for all I. Okay, now if suppose we are doing this partial derivative of xi with respect to this xi. Now if suppose this is xi dash greater than equal to 0, suppose it is of this form. So this partial derivative of xi dash with respect to xi will be equal to 1 if I dash is equal to I, otherwise this partial derivative will be equal to 0. So this partial derivative will be equal to 0 if I dash is not equal to I. So that is why there is a single term here, ui double dash times 1 here, okay, because this partial derivative is equal to 1, and since only for that case when we have the same index there will be non-zero term, otherwise we will be having 0 here. That is why there is a single term here. Okay. Now for this set of constraints we have these conditions that uj should be greater than equal to 0, we already know this. Then we have these set of constraints that if there is any non-binding constraint, that is bj minus summation hij xi star is not equal to 0, then uj should be forced to be 0. So that is why we have this constraint, and whatever solution that we are getting, it should satisfy the constraints that we have. So that is why we have summation hij xi star greater than equal to bj. Then similarly for this set of constraints here, that is minus summation hij xi is greater than equal to minus bj for all j. So again we have uj dash greater than equal to 0 because we have these parameters for this set of constraints, and then again this constraint is ensuring that if we have a non-binding constraint, then uj dash should be equal to 0, and whatever the solution we get, it should be feasible. So that is why we have these constraints. And for the set of non-negativity constraints that we have here, so for that we have again this ui double dash greater than equal to 0, and now here since this constraint is of this form x I greater than equal to 0, so that is why there is this single term here getting multiplied by ui double dash here. So we do not have any constant, I mean the constant is 0 in this case x, when we have constraint like xi greater than equal to 0 for all I. So this is 0, so that is why we just have xi star here, and then again the solution should be feasible. So that is why we have xi star greater than equal to 0. Okay. So what we have done here is that we have written down the same KKT conditions that we had derived, but for this special kind of optimization class, the one which has linear equality constraints and non-negativity constraints. And now what we will be doing is that we will be further simplifying these conditions. So we will realize that the final set of conditions that we get from analyzing these will be much simpler than what we originally start with, these ones. Okay. So let us move forward. Maybe before moving forward, I can give some insights from here itself. So one thing is that the optimization problem already has these constraints, that summation hij xi is equal to bj for all j, and this is for all I. Okay. So if that is the case, then if xi star is a solution that we want to find, since it has to be feasible, I mean this is a stationary solution, so this is equal to 0 because of this constraint. Okay, because xi star has to satisfy the constraints. Similarly this will also be equal to 0. So that is why this constraint and this constraint is not required, because they are not imposing any condition on uj and uj dash. Okay. Now the other thing is that these two constraints, summation hij xi star greater than equal to bj and minus summation hij xi star greater than equal to minus bj, can be compactly written as the linear equality constraint that we have seen before also. Okay. And another thing that we will be doing is that we will be introducing a new parameter uj star that will be equal to uj minus uj dash. Okay. So when we do that, then we can simplify this term here and we can just write it as equal to summation uj star hij, and the summation is again going from j equal to 1 till capital J. Okay, so we are replaced these two parameters by a single parameter uj star. Okay. Okay, so let us move forward here. So the next few points will be saying the same thing that which I have been saying. So summation hij xi star is equal to bj holds, and therefore these two constraints can be ignored, because if this is already equal to 0, whatever value uj takes, it is not an issue. I mean it can take any value. Similarly, if this term in the bracket is equal to 0, then there is no restriction on uj dash, so then it is not a constraint actually. So there is no need of this. Similarly, if we define uj star equal to uj minus uj dash that I just mentioned before, so then since there is this restriction that uj is greater than equal to 0 and uj dash is also greater than equal to 0, so uj star are unrestricted variables. Okay, so we do not need constraints of this form that uj star greater than equal to 0. Okay. And since we are replacing uj and uj dash with uj star, so we do not also need those constraints that uj is greater than equal to 0, uj dash is greater than equal to 0. So therefore, we can simplify the KKT conditions that we saw in the previous slide into this form here. So the first set of conditions has been simplified by replacing uj minus uj dash by uj star. This is that term here, okay. And the next two set of constraints have been just been replaced by this, okay. So we had previously split this equality constraints into two inequality constraints, and now we have come back to this, and we have already seen that these two kind of constraints are not required because bj minus summation hij xi star is anyway equal to 0, and since we have replaced uj and uj dash by uj star here, so that is why you do not require these conditions also, that uj greater than equal to 0, uj dash greater than equal to 0. And this last set of conditions is the same here that was before, that is ui double dash greater than equal to 0 and so on, okay. Now what we will be doing is that there is one final step that needs to be done. So we will be replacing the value of ui dash that we get from here, that is ui double dash from here. So we will be replacing the value of ui double dash from here with this term minus this term, okay, and we will be putting the value of ui double dash here and here. So let us do that. So substituting the value of ui double dash to be equal to the partial derivative of z with respect to xi minus this summation uj star hij in ui double dash greater than equal to 0 and ui double dash xi star equal to 0, we get this condition. So if you replace ui double dash this value here, you will be getting this. This is the first condition, okay, and we know that ui double dash is greater than equal to 0, so we get this condition, okay. And then we have this constraint with that summation hij xi star is equal to bj for all j, and then xi star is greater than equal to 0. So these are the constraints that we originally had, okay, and these are the additional conditions that we get. So these are this overall are the KKT conditions when we have non-negativity and linear equality constraints, okay. So you can see that this is much more simpler than what we had seen when we had just started. So 2 slides back we had just started with the KKT conditions, and now here we are. So one thing is that you just have now this one parameter uj star instead of this uj dash, uj double dash and ui double dash, okay. So the number of parameters have reduced, the number of conditions that are there have also reduced. We have thrown away a lot of conditions also that were not required, okay. So these are much simpler now. So these conditions are called the KKT conditions for optimization problems with non-negativity and linear equality constraints that I mentioned. So in these conditions ui uj star are the variables along with xi star, and these variables uj star are called Lagrange multipliers, and the number of these variables uj star are equal to the number of equality constraints, okay. So with this we will be ending this lecture here, and then we will be continuing in the next lecture. Thank you.